Good morning, my audience. My name is Ajibola Arewa. I hold a PhD in finance. I lecture in the Department of Finance, Lagos State University. This morning I want to train you on the application of Python for estimating Lyapunov exponent, interpretation and application for practical study. So the title of my training is Python application for the estimation of Lyapunov exponent, interpretation and implication for practical study. The content for discussion. Content for discussion. What is a Lyapunov exponent? What does it mean? Lyapunov coefficient. What is the meaning? 2. Mathematical formula of Lyapunov exponent. Mathematical formula for Lyapunov exponent, for calculating Lyapunov exponent based on ODE, ordinary differential equation, ODE. 3. Mathematical formula for calculating Lyapunov exponent or coefficient based on time series equation such as AMA, autoregressive moving average model. 4. Mathematical formula based on SDE, stochastic differential equation. 5. Application of Lyapunov exponent in financial markets. Application of Lyapunov exponent in financial markets. 6. Python code to estimate Lyapunov exponents. 7. Python code to estimate Lyapunov exponent or coefficient on rolling windows. When we get to this point, I will explain what we mean by rolling windows. Then plotting the graphs. Let's take the first one. What is Lyapunov exponent? Lyapunov exponent or coefficient is a gauge or is a measure that shows the response or the sensitivity of a system to its initial condition. So it measures, Lyapunov exponent measures how a system responds to its initial condition. A system here can be in a market price, stock price, commodity price, stock return, interest rate, exchange rate, or any other variable. In social sciences, variables in management sciences, variable in engineering, variable in sciences, biology, agriculture, So it measures how variables respond to its initial condition. Alternatively, Lyapunov exponent or coefficient is a score that quantifies the rate of diversion or convection between two infinitesimal or infinitesimally close trajectories in a dynamic system. So it is a score that measures how two infinitesimally close trajectories diverge or convex over time in a dynamic system. It is very, very crucial to chaotic system. And it is used to measure how chaotic a system is, how chaotic an economy is. It is used to measure how chaotic a financial market, how chaotic financial markets are. Financial markets such as stock market, bond markets, derivative markets, foreign exchange markets, and interest rate markets, or money market. So it measures how chaotic a particular market is. I will provide further explanation on this when we get to explanations of results. Now, mathematical derivation of the formulas of Lyapunov exponent is just a coefficient or a score that can be computed given a variable or values of variables. Now, it can be computed first using ODE, ordinary differential equation. What is meant by ordinary differential equation? An ordinary differential equation is an equation that doesn't contain a random part. It only has a deterministic trend, or a deterministic part, a growth part, but it doesn't have a random part. It has a deterministic part. In a dynamic system where we only have a deterministic part, no stochastic part, then such system is referred to dynamic or deterministic dynamical system. Now, mathematically, the formula for calculating Lyapunov exponent can be derived from ordinary differential equation, ODE. This is based on the assumption that no term of the equation has a random part or shock, meaning that the assumption of deterministic dynamical system. Thus, the formula can be summarized as. Now, I have said this, that in an ordinary differential equation, you don't have a random part, but we have a deterministic trend, a deterministic part. Now, the formula can be summarized as lambda is equal to lim till moving to infinity 1 over t in the x till the x naught. All we have that formula asks lambda is equal to taking the limit as t moving to infinity 1 over t in the xt minus in the x naught, where the xt is equals to the x naught multiplied by exponential raised to power lambda t, where your lambda is the exponential or is the Lyapunov exponent. Then the st is the separation after time t. The s naught is the infinitesimal perturbation. Let me repeat that. Your lambda is your Lyapunov exponent, which I've just explained. That it is the measure of diffraction or convection between two trajectories. It measures how two trajectories will go apart, or it measures whether there is possibility of converging. The dxt, delta xt, is separable after time t. That is the change after a specific period. The change in the system after a specific period. The ds naught is the initial change. Infinitesimal perturbation. Perturbation means small change. Infinitesimal perturbation. That's change. So perturbations here means change. So ds naught is the initial change. Then dst is the change after time t. T can be 3 months, can be 4 months, can be 6 months. Depends on the numbers of observations you have. Now computing the exponent from a time series. Then the exponent can also be computed from time series equation, such as AMA. The formula for computing the Lyapunov exponent, lambda, can still be derived from a time series regression model like AMA, ARIMA, AFIMA, etc. It is important to know that the conventional Lyapunov exponent is based on or is designed for a deterministic system. However, it can be extended or expanded, prettily expanded, to a stochastic system, such as ARIMA and AFIMA. So what I am saying here is that traditionally, the Lyapunov exponent is meant for a deterministic system. That is, a system that does not incorporate uncertainty, stochasticity, randomness. A system that is absolutely for deterministic trend, growth. That is what Lyapunov exponent is meant for. But now it has been expanded to stochastic system, such as AFIMA, ARIMA, AMA etc. Even AMA with moving average error, and all of those stochastic systems, we can derive Lyapunov exponent from them. This is possible, and this possibility is generally referred to Lyapunov exponent of a stochastic differential equation. Yes, Lyapunov exponent of stochastic difference equation. We should be aware that the derivation for Lyapunov exponent in such stochastic system is not direct, and in the derivation process, the noise element is eliminated, or the stochastic part is terminated. Thus, the hitherto stochastic system gives way to linear deterministic dynamical system. In summary, the formula is expressed as. Now, what we have here is this. Now, I've just explained that Lyapunov exponent is designed for a deterministic system. But prettily speaking, it has been expanded. It has been generalized to the stochastic system. However, in deriving Lyapunov exponent from a stochastic system such as AMA or ARIMA, the noising element or the noise element is eliminated. The stochastic part is eliminated. Therefore, the hitherto stochastic system gives way to a linear deterministic dynamical system. In summary, the formula for deriving Lyapunov exponent from a stochastic system based on AMA or AFIMA is given as lambda, taking the limit as still moving to infinity, 1 over t in A, that is a matrix, raised to power t, delta x naught is equal to in P, open bracket and close A. That A is a maximum absolute eigenvalue or the spectral radius obtained from ARO coefficient or companion coefficient. So let me repeat this. The PA is maximum absolute eigenvalue of A or the spectral radius. And the A itself is the ARO coefficient companion matrix or companion matrix of ARO coefficient. For this, given a typical time series, we can use this method to compute its Lyapunov exponent. Now we move to the next page, that's page 5. Then we now have a mathematical formula for deriving a Lyapunov exponent based on stochastic differential equation. Now, let me just iterate that a conventional deterministic dynamical Lyapunov exponent of the ODA base has been augmented to stochastic dynamic Lyapunov exponent that is rooted on stochastic differential equation SD. The assumption here is that at least one of the terms in the equation contains a random part uncertainty. So the first assumption is relaxed. The OD assumption is relaxed, that none of the part of the equation has a random part, no uncertainty. But that assumption has been relaxed because the word itself, the system of the word, is full of uncertainty. So stochasticity needs to be incorporated. and that give rise to stochastic differential equation. Now, computing Lyapunov exponent from the stochastic differential equation is summarized as lambda is equals to lim, taking the limit as t moving to infinity, 1 over t, expectation, bracket open and close, in the xt or delta xt, delta x naught is equals to u minus mu minus 1 over 2 variance. Now let's have the terms defined. U is the expected or average value, and this is the variance, and then we can see that if you have a time series, we compute the mean value, then we compute the variance. We can simply get the Lyapunov exponent. A very simple formula. Though this formula is derived from SDE equation using Ito calculus, Ito lemma, and Taylor series expansion. This is summarized formula. U minus half of variance. So if you have a time series, you obtain the expected value, that is the average value, then you obtain the variance. Then by the time you divide the variance by 2 and you minus it from the average value, you have your Lyapunov exponent. That means that the exponent will increase by increase in your expected value, while the exponent will decrease by increase in variance. So when variance increases, the Lyapunov exponent decreases. When expected value increases, then Lyapunov exponent increases simultaneously. Well, if you may need additional coaching on this, how this formula is derived, you can contact me on my WhatsApp number, which is +234 80 60 96 20 48, or you can send me an email message to ajibola.arewa@lasso.edu.ng. Now, page 6. This is page 6. So page 6, we have Python code to estimate a Lyapunov exponent or coefficient. We can get the code by asking ChatGPT, give the instruction to Chat, and Chat will give you the code on how to compute Lyapunov exponents. Now, the first one we have here is give me the Python code to estimate Lyapunov exponent. My data are saved in my desktop using CSV. Username is Dell. File name is market1_data. And my variable name is price. That we are now using the algorithm of Rosenstiel. And this algorithm is meant for a deterministic system. However, before we execute this instruction, we need to download the data of our choice. And I want to make Nigeria market as a sample for this study. And those of you in America, in Europe, in South Africa, and some other countries, you can use your own market for example. Let's use Nigerian market for example, and then before that, let me quickly download the data for this experiment. Download the data from this experiment. So to do that, now I said before executing this command, ensure that your data are already saved in this direction or path described above. We have given a direction where our data are saved, desktop, and then the username Dell, the file name market1 underscore data. That must be achieved before executing code in Python, so that Python will know where your data are saved. Now let us quickly download the data for Nigeria. Then now calculate the exponent of Nigeria stock market. I will ask ChatGPT now, give me the link to manually download Nigeria Daily All Share Index from 2015 to 2024. This is my specified period, 2015 to 2024. I will just copy this, and I will execute this in charts. I will go to charts, go to chart to execute it. My default browser is Chrome. Then I will open charts. Then I'll paste it there. What is my instruction? Give it to ChatGPT. Give me the link to manually download Nigeria Daily All Share Index from 2015 to 2024. I mean daily data, not monthly data. So I enter. Now I want to have the link. Yes, this is my result. So there are so many places where we can download this data from. We have from Nigeria Exchange, official historical data. We have investing.com. We have CEIC data, monthly all share index. Then we have trading economics historical index data. We have cargo, archive data. I would prefer to take the first one. Then this is the first one. So this first one will give me the link where Nigeria All Share Index data can be downloaded for. So you execute it. Now once you click on it, look at what I've done. You click on this place. It will take you to where the data can be downloaded from. Look at it now. This is investing.com. And then you quickly move to this where the data can be downloaded. Then you click here. You click this. From 2015. From 2015, you quickly check where is 2015. 2015. You select 2015 here, and then you select the dates, you enter, then you come here, you select 2024 here, the month and the date, you enter, then you apply. Once you apply, it will be downloaded, and if it's downloaded, you save it in your desktop. This is my own here. So I've already saved it here. Date, price. It might come with volume, head of opening price, closing price, volume. You may decide to delete them to be left with only price. So let me close this, and then you have to save it with market1_data CSV. market1_data CSV. You can use any other thing. It could be stock_data, then save with CSV. So you come here, save as, you go to desktop. Then when you get to desktop, here you click here to change it to CSV. There you put market_data, or you can change the name and use your preferred name, file name. So if that is done, that means that your data is right now in desktop, and your username is Dell. Because I'm using Dell, your own could be HP. Depends on the Windows you are using, or depends on the laptop you are using. I'm using Dell. Now, having done that, you now have your data in desktop saved using CSV. So the next thing is to get the code to compute the Lyapunov exponent based on these equations or algorithms. First, I want to use Rosenstein algorithm, Rosenstein's method. Let me use that. So what I will just do is to give this instruction to chat. Give me the Python code to estimate Lyapunov exponent. My data are saved in my desktop using CSV. I've said that. Username is Dell. File name is market_data, and my variable name is price. Now you can see this P is capital. So if your own is not capital, if it is small letter, you put small letter here. So exactly what your variable name is what should be here. Then you copy this, and then Ctrl+C. You quickly move to where you have your chart to execute that command. So you just paste it here. Just Ctrl+V and X. So this is what you are going to have. So it's giving you step by step, and there are two options here. Now the first one is to estimate the Lyapunov exponent from your time series data in this. Make market price data. We need to follow a few steps. The Lyapunov exponent helps us measure this. Okay, of course we know that. So let's just look at the code instead of going through those explanations. So which one are we going to? There are two options here. You can take any of the options. Now me, I will just prefer, I will prefer option B. So I will just go to option B. Let me just select option B. I will prefer option B. So I will just move down. Say I prefer this option. So now that is option B. Option B. Now this is the code for option B. This is the code for option B. Here, first you have to open your prompts to execute this bash before executing the code in Jupyter Notebook. Let's do that very quickly. This is my Anaconda prompt. You open it. Then you can minimize. Open Jupyter Notebook also, launch it out. There you can minimize the navigator. You can minimize the navigator. I'm still expecting. Yeah, it has come. The notebook is loading on my default browser. So let's wait patiently. Okay. There's it. Then I go to File, select New, then select Python file. Then rename this. Rename, I can rename 00001 and 2. Then rename. It appears here. If it doesn't appear here, it means that you have used the number before. So you need to use a number that you have not used before. You can't repeat numbers. Then I move to File. I will select Create Console for Editor. So select. It will take a while. Just wait patiently. Now, this is the place to put my command. Remember, we are computing Lyapunov exponents based on a deterministic system. That is the assumption that stochastic process does not exist using Rostelli's algorithm. Now, I will move here to copy the code. Now, first of all, let me go to Patch, go to Anaconda prompt, copy. Then I'll go to the prompts. There's the prompts. Then Control V. So, just wait a bit and see what happened. Good. Then thereafter, I've passed patch it, then I minimize. If I minimize, then I would now go to where we have the code, then I will just copy that. Copy that, then copy this. So after that, I will come and then execute it in Python. So let me execute it in Python, and then I go to Python to execute. Ctrl V to paste, then Shift Enter to execute. So you may wait and see what will be the result. Yes. Now we have done that. Look at what we have. This is the Lyapunov Exponent, 0.114, and then the time series graph is given. This is the Lyapunov Exponent. But let's go back and see. Now, there's another structure. If you want to try a resistant method, you can use this. So let's look at it, because the method we want to execute, resistant algorithm. So let's see that. You copy this, and then we'll come here to execute it. Control, then Shift, you enter. Now it comes with this error. What you do is a type error. So you do this. If anytime you have error like this, you just copy, then you move back to charts to ask that you are confronted with this error. Then you paste and enter. Now, look at what you have. It said, usually, this error usually occurs in the loops library when the input data is not a proper numeric type like floats or int64, but instead include object types or strings. This often happens if the price column contains non-numeric values like missing entries, symbols, or formatted strings. So what do? In this case, let me see the next thing to fix. So fizzing. So there's a fizzing. I think he has fixed the problem. So let's copy this. Move to execute. Ctrl V, Shift, Enter. Yes, now we've gotten the result based on the resistant algorithm. This is the result. I think there's not much difference. We still have 0.114 as our largest Lyapunov coefficient. Now, I will give interpretation to that when it comes to the section for interpretation. Now, let's move further. We have the next one is based on based on stochastic system, SDE. So what I will do is to copy this. Now look at this instruction. Give me the Python code to estimate Lyapunov exponent based on stochastic dynamical system. My data are saved in my desktop using CSV. Username is there. File name is market_data. My variable name is price. Control C. The reason why I am giving this instruction is to inform or pre-inform Python that these are the place, or this is the place that my data are saved. If that instruction is not given to Python, you will not get results. Let's go to chart. We go to chart. We are middlemen between chart and Python. We go to chart to get the code. Then we move to Python to execute. Let's get the code from chart. Now, Python code for calculating a Lyapunov exponent based on stochastic dynamic equations. This is what we have. So let's copy. Then we move to here to execute. Ctrl V, Shift, Enter. Now what do we have? We have an error. Now we can simply copy this error and take it to chart to fix the problem for us. Ctrl V, Enter. Oh, it said you are absolutely right. The node package does not have Lyapunov this function. That was an error in the previous response. Corrected Python code. Now, this is the corrected Python code. Let's see that. So, copy this and then go back to execute. Ctrl V, Shift, Enter. Yes, we have this as our results. We have this as our result, but this is not exactly what I want. It's still rotated method, but this is not the method I want. Then I will go back. And ask charts that the method should be based. The method should be based on stochastic dynamic equation. Probably he has lost the memory. Let me say the method should be based on stochastic differential equation. Stochastic differential equation, not not let me get the correct name, not Rose stem algorithm. No, not Rose stem algorithm. So now I have instructed chat, this is what I want. So thank for the clarification. You are interested in computing the Lyapunov exponent based on stochastic differential equation, SDE, not using deterministic time series algorithm. Say yes, that's what I want. So let's see. I think he has gotten the structure properly now. Okay, you can see all this. And then let's copy the code. Let's copy the code. Let's copy the code and then execute. Yes, this is what we have. This is what we have. You can see now we have estimated Lyapunov exponent SDE based minus 0.00229. Then we have the estimated expected result, the expected value or mean or average value, then estimated variance or standard deviation. These are the values for standard deviation, values for mean, and this is the value for Lyapunov exponent based on stochastic dynamic or stochastic differential equation minus 0.000229. Actually, if you get the half of this value, you minus it from this, you will have this. Stochastic Lyapunov exponent estimation. So this is what we have. This is very good. These are our results, but no interpretation yet. I will do that later. Now let's go back. And then the next one is to compute the Lyapunov exponent based on ordinary differential equation. It is also a deterministic system. So let me give that instruction. Let me give that instruction to chat so that I can get the code to execute this in Python. Then I move again, go to chat, then I paste, then I enter. Now, yes. So I may not need to be reading all this.